Hello, and welcome to the Student Academic Learning Services Solving Two-Step Stoichiometric Problems video. In this video, we're going to use the same method as introduced to you in the introductory video to solve a more complex two-step problem. So, let's get started. Let's recall the difference between a one-step and a two-step problem. In a one-step problem, the question will simply be asking you to convert from the number of moles of a given substance to the moles of the required substance. In other words, any data provided to you in the problem will be in moles already, and it will ask you to find the number of moles of some other reaction participant, hence only one step needed to find your answer. Now, in a two-step problem, there could be two different situations. Either you are converting from the moles of the given to either the mass, number of particles, or the volume of the required substance, which involves the boxes and arrows selected by the purple bracket here. And as you can see, that only selects two arrows, which that is the whole reason why this is called a two-step problem. The other situation is that you may be converting from the mass, number of particles, or the volume of a given substance to the number of moles of the required substance, which consequently involves only the boxes and arrows selected by the green bracket here. Either way, you require two steps to obtain your final answer. Here is the method for solving stoichiometric problems, which was introduced in the Introduction to Stoichiometry video. Whether you're dealing with a one-step, two-step, or three-step problem, you can always refer to this method. The only difference that you will notice is, depending on which type of question you are working with, some questions require step 2 and 4, whereas others don't. So let's just proceed and take a look at a two-step problem now. A typical stoichiometric problem will appear something like this. You'll be given a chemical reaction, either balanced or not balanced, as well as a problem statement. This one asks, how many grams of ammonia will be produced by the reaction of 4.0 moles of hydrogen gas? It's essentially asking, based on the ratio of the substances in this reaction, once it's balanced, what mass of ammonia can we produce if we're given this particular quantity of hydrogen gas? So it's all very dependent on ratios. Okay, so there might be a number of questions running through your mind right now. Where do I begin? How do I know it's a two-step problem? What are my given and required substances? Etc., etc. Well, first of all, take a deep breath. Yes, there's lots to take in with stoichiometry, but this is why it's best to have a step-by-step approach. So, if you will, let's concentrate on their method for now, and you'll see that everything will just fall into place from there. The first step is to start with a balanced chemical equation. Can you pause the video for a moment and examine the left and right sides of this reaction? All finished? Well, hopefully you determined that our equation is off balance and it needs some new coefficients. Feel free to pause the video again now and attempt to balance this equation by yourself. Great. Now, hopefully these are the new coefficients that you came up with after you balanced it. Now let's move on to step 2. Step number 2 indicates that, if necessary, you must now convert the given information into moles. Wait. Before you decide whether it's necessary or not, this brings up a good point. Which substance is the given and which is the required? Well, in every type of problem, you will be given one piece of data, and whichever substance that data is describing is going to be your given substance. In this statement, they are telling us that there are 4.0 moles of hydrogen gas, so that means that hydrogen gas is our given substance. Secondly, this statement will be asking for some quantity of another substance from the reaction. In this case, it's stating how many grams of ammonia. So ammonia, for this example, is the required substance. Back to step 2 then. Is it necessary to convert the given data into moles? Absolutely not. because in this statement it's already given to us in moles. Moving on then. Step 3 is to calculate the moles of the required substance using a mole ratio. So this is actually our very first calculation. And what we need to do to convert from moles of given to moles of required is multiply the moles of the given, which is right from the question, by the proper mole ratio from the balanced chemical equation. And here's just a reminder of how you can always find the proper mole ratio. You're always going to want moles of your required substance, so the coefficient of that from the balanced equation, over the moles of the given substance in the balanced chemical equation. So just to remind you of that, it's right there. Okay, so now what we're going to do is we're going to take the 4.0 moles of hydrogen gas and we'll multiply it by our mole ratio. So moles of required, so there's 2 moles of ammonia in the balanced chemical equation over, and from the coefficient here, there's 3 moles of hydrogen gas. So now you have your mole ratio set up. And the reason why we do it this way is now we can cancel out the moles of the given substance. So moles of hydrogen gas get canceled out. We can run this calculation, so 4.0 times 2 over 3, and the number we end up with is 2.7, and it's 2.7 moles of ammonia, which is our required substance. So now you've completed step 3. Before we move on, just a little flashback to the diagram that I showed you. This represents the 2 calculations we need to make right here. And so far, we've completed the first one because we've converted from the moles of the given substance to the moles of the required substance. Next, we're going to be converting from the moles of the required substance to the grams of the required substance, because this is what the question is asking us for. And take a look right here above the arrow. In order to get from moles to grams, we'll need to use the molar mass of the required substance. But the question is, what do we do with this molar mass? So let's take a look at that. Remember, anytime you need to use molar mass, the values can be obtained from a periodic table. They are the numbers listed directly below the elemental symbols. So let's get the molar mass for our required substance, ammonia. Ammonia contains 1 nitrogen, and the value for that is 14.01. And it also contains 3 hydrogens. So we'll have to multiply the molar mass for hydrogen by 3. So the total for hydrogen is 3.03. Now if we total these up, the total molar mass for ammonia then is 17.04 grams per mole. Now you'll notice the units for molar mass, grams over moles, which is actually saying grams per mole. So this simply means that for every 1 mole of ammonia, the mass is 17.04 grams. We can also write it like this: 17.04 grams over 1 mole. This will work nicely for our next calculation then. So remember, we just determined in step 3 that because of the mole ratio in this equation, there are actually 2.7 moles of ammonia, not only 1. So here's how we can arrive at our actual mass then. We're going to take the molar mass, 17.04 grams over 1 mole, and multiply it by 2.7 moles. This way you'll be able to cancel out moles, and when you actually multiply 17.04 by 2.7, you get the number 46.01. And now it's just grams because we've canceled out moles. or if you want to use the correct significant figures, which you always should, it actually rounds to 46.0 grams of ammonia. Okay, so we've completed all 4 steps, and we were able to find that if 4 moles of hydrogen gas reacted in our given reaction, then 46.0 grams of ammonia would end up being produced. Now that we've solved the two-step problem, I just want to make sure you can see the pattern here. So in any given problem, if you're asked to convert between one reaction participant and another from a balanced reaction, I'd like you to realize that in order to jump from one substance to another, you need some sort of a stepping stone. And the stepping stone you're always going to use is the mole ratio. So in ours, to go from hydrogen gas to ammonia, we needed a stepping stone, which was the mole ratio. But of course, in order to use that mole ratio, your data has to be in moles first. And it ends up being in moles too. So that's why you need to use the different types of conversions, because your data isn't always provided to you in moles, and you may not need to leave it in moles. You may want to leave it in something like grams or volume, depending on what the question's asking for. So that's why having something to refer to like this diagram can help you get used to the different conversions you need to make. So for example, when converting between mole and mass, you're always using molar mass, but when you go from mole to mass, you're multiplying by the molar mass. And when going back from mass to the mole, you're actually dividing, because you're like inverting that unit factor. And the same thing applies for whether you're converting between moles and volume or moles and particles. You're always either multiplying or dividing by that value. And from moles to volumes, it's the 22.4 liters, and from moles to particles, it's Avogadro's constant, 6.02 times 10 to the 23. So I do suggest you write out some sort of a reference for yourself for your conversions, and it'll make it a lot easier once you decide how you solve your problem. It'll make it a lot easier to just go ahead and make those calculations. Well, that brings us to the end of the video on how to solve a two-step stoichiometric problem. If you have any questions regarding the material that was just covered, please come to the South Center, located in room 204 of the Student Services Building, and then you can make an appointment with the appropriate learning skills advisor. Thank you very much for watching.